All right, this is conservation of energy number 2. We are going to add friction to the system. So let's say we have a situation of a ground and then a ramp of some height. All right, let's say the question is about a block that's sliding with some velocity, and the question is, how high is it going to go? That's the question. Let's also say we know mu. So we have an idea of the coefficient of friction. Let's declare this frictionless and friction's on the incline. All right. So our conservation says energy initial equals energy final plus work done by something. Notice that it's a plus here. That's because we know the work done by friction is going to take away from the original value. So if this is 10 joules, this is going to be less than 10 joules because that thing just stole the rest. So the amount of work done by friction plus whatever the block is doing will equal the original 10 joules, for example. So this is how we're going to set this up. So initially, the block is just sliding, which means the only thing it's doing is moving. No gravitational potential and no springs. Now the moment we strike here, it's going to start going up the plane. Now this is the key. I want to know, so this is phase 1, that's phase 2. When it reaches maximum height, what's the velocity? The velocity will be 0, so that means there's no kinetic energy. So if I just, for the sake of argument, put in everything possible, that's a 0. It's not moving. So a lot of times, you can always write them all out like this, and then declare what's 0, so we could formally do potential energy of a spring, which is also 0 because there are no springs here. But that is one option, so that you keep track of all the energy at all times. Or we can just go straight to the idea of, well, I know there's no kinetic because it's not moving. At maximum height it stops. I've got nothing but potential energy plus work done, and I'll do a subnote of by friction. Which means I have to know theta, right? Because buried in friction is the normal. So when I solve this, I just substitute in 1/2 mass velocity squared equals potential energy, which is mass, gravity, height. That's the height of interest, plus the work done by friction. And because the work done by friction is parallel to the plane, that's pretty straightforward. So we also need to know d of the ramp. So I'll declare that as d for the work done going up the ramp. So it'll be the force of friction times d the ramp. The force of friction is going to be buried in the y-axis. Right, because when we sub in, force of friction is mu normal. Distance is right there, so we're going to have to know a little bit something about that height, which is not clear. If you notice, what I'm going to have to do is, in these kind of questions, I got to give you height, I got to give you some information about the ramp, such as either the slice of the ramp or the angle. Most likely it's going to be the angle. If I tell you I want to know maximum height, that means I don't know what the distance up the ramp is, but I'll have to tell you what the angle is. So the key to the normal, if you remember we'll do d, but let's do d in terms of height. So if we look at our triangle, the reason why I want to do that is because I don't want an equation with 2 unknowns in it. I'm going to substitute in so that I have nothing but the height that it stops moving. If I look at my triangle, the only trig function that gives me the ramp, the distance up the ramp, and the height is tangent. So I'm going to solve, so tangent will be, or I'm sorry, this is a sine function. Sorry. Height over d. So when I solve for height, it becomes, oh, I'm solving for d, sorry. So I solve for d, so this is sine theta equals opposite over hypotenuse. I'm subbing in for d, so that means I solve for d, so that means d equals h height over sine theta, which then will turn into h over sine theta. Now, the only thing I don't know is height at this point. Also, this is y-axis stuff. You'll have to use your Newton's laws in the y-axis to get a handle on that normal. So go back into your notes about doing things in inclines and looking at the force of friction on an incline to see how to deal with that in case you forgot.